Moving fluids form complicated patterns. These patterns are often quite surprising. What appears to be a small shift in system geometry can change the entire flow pattern. But it is almost never possible to predict the real flow pattern on theoretical grounds alone. We need other approaches. One of the most efficient is flow visualization, direct observation of the flow field. Visualization is an important tool in establishing flow models as a basis for mathematical models. We can use it for direct solution of engineering problems and also as an aid to understanding the concepts of fluid motion. An open surface water channel, such as you see here, is often used in flow visualization. It consists of an inlet section which distributes the flow evenly, fixed outer walls, and adjustable inner walls so that we can achieve any passage shape desired. The flow leaves through a porous exit section to give an even velocity profile. There are a number of visualization methods that can be used with a water channel like this. We can use dye injection. We can use surface powder on the water. First thing we're going to use here, however, is the hydrogen bubble method. If we connect a DC voltage to a very fine wire, here 2 mils, and put the wire in the water, electrolysis forms extremely small hydrogen bubbles which are swept off by the flow. Most of these bubbles are small enough so that they follow the flow quite accurately. A few large bubbles are also formed. We ignore them in observing the flow pattern. Here you see a probe with multiple thin fingers which makes many fine lines. Another kind of probe is a single wire with sections insulated so that we see bands of bubbles coming off the probe. In order to interpret flow pictures, we need to be quite clear about 4 concepts. These relate the pictures to the kinematic description of the flow field. The first concept is the path line. A path line is the trajectory or path of a given fluid element. Here we mark a small element with bubbles so that we can follow its path. If we took a time exposure, we would make the entire path visible. Instead, we superpose a path line, and you can check for yourself that each of these squares follows it. A streak line is a little different. It is the instantaneous locus or trace of all the fluid elements that pass through a given fixed point in space. If we run a short, uninsulated section of a bubble wire steadily, it shows us a streak line. In steady flow, each particle coming past the fixed point moves down the same path, and therefore the streak line is identical to the path line. We can check this by resuperposing the path line you saw earlier. Often it is useful to use multiple streak lines to observe a flow field. We can make them with the multiple finger wire you saw before. The third concept we need is the timeline. A timeline is defined as the instantaneous location of a line of fluid particles marked earlier at a prescribed location in the flow. These lines are usually most useful if the marking location is normal to the flow direction, since then the location of the timeline, a short time later, shows the velocity profile of the flow field. Here we apply the timeline technique to a steady flow past an airfoil. Near the angle which gives zero lift, the portion of the timeline passing above the airfoil rejoins the portion passing beneath at the trailing edge, except for the narrow boundary layer region where the flow is retarded by friction. Since the distance around either side of the airfoil is approximately the same, the timelines show that the average speed above the airfoil is approximately the same as beneath it. When the airfoil is set at angles which give large lift, the portion of the timeline passing above the airfoil outruns the portion beneath. The velocity is higher near the upper surface. At negative incidence, the effects are reversed. The fourth concept we need is the streamline. A streamline is defined as any line that at a given instant is everywhere tangent to the velocity vectors of the flow field. The streamline is essentially a mathematical idea and is very useful in many fluid flow analyses, but there's no way to make a streamline directly visible. You've seen that in steady flow, the path line and the streak line are the same, and you might suspect that the streamlines would coincide with them also. This is in fact the case. Consider a particle moving along in steady flow. As you saw, each particle moves down the same path line, so that it's always moving down this path towards the particle ahead of it. This means it is always tangent to the path, and that is how we defined a streamline. So in steady flow, the streamline, the streak line, and the path line are all the same, and we can use either streak lines or path lines to show us the streamline pattern. Another thing we often need is the velocity vector field itself. We can find the velocity field by using what I call combined time streak markers. The bubble squares you see here are such markers, and they have a number of useful properties that you can prove for yourself. The sides of the markers are streak lines. In steady flow, the sides show the streamline pattern. The fronts and backs of the markers are timelines. In a two-dimensional incompressible flow, the area of each marker is forever constant. Since the time interval for a given marker to pass any fixed point in space is also constant, the length from the front to the back of a marker at any location is a measure of average velocity in that region. Now consider for a moment an unsteady flow, like the one you see here past an oscillating plate. Do you think that in this case the streak line or the path line will be the same as the streamlines? Let's look at a path line and see. Here is a single marked element entering at a fixed time in the cycle of a plate. As before, we superpose its path line. Now compare the path line with a succession of instantaneous streak lines entering through the same point. None of the instantaneous streak lines coincides with the path line. Here is a second element entering through the same point, but starting at a different time in the cycle of the plate. Notice that its path line crosses that of the first element almost at right angles, and it leaves around the other side of the plate. Now you see elements marked at both times in the cycle of the plate. If we superpose the path line of the second element and compare it with a set of streak lines through the same point, you can see that none of them coincide with the second path line either. Now let's see about the streamlines. In order to find the streamlines, we need the direction of the velocity at each point. We can find this from combined time streak markers, such as you see here. If we take a transparency of one frame of the multiple time streak lines and overlay on it another transparency taken a few moments later, we can connect the endpoints of the streak lines and show the particle paths for short time intervals. Here you see the short dashes made by connecting the endpoints of the time streak lines. They show us the velocity direction at each point. If we draw lines parallel to them, these are the streamlines. The total streamline picture you see here is for the same instant that the first particle we observed with a path line entered the frame. The dotted streamline is the one that passes through the same point. If we compare the dotted streamline with the path line through the same point and at the same instant in time, you see they are quite different. If we compare the dotted streamline with a set of streak lines entering through the same point, they do not coincide either. In a transient flow, the streak line, the path line, and the streamline are all different. If the streak lines move sidewise, as you see here, then the flow is transient, and we cannot use the streak lines for streamlines. In a transient flow, we must work out the velocity field from some kind of combined time streak markers. We've seen one way to make the flow visible. Now let's see how to use this information to solve engineering problems and as a basis for mathematical analysis. As an example, let's consider straight-wall diffusers. As you probably know, a diffuser is any passage that decelerates the flow and causes a rise in pressure. In subsonic flow, the diffuser is merely a diverging passage. Between 1900 and about 1950, a number of studies showed that if we increase the divergence angle of the diffuser 2 theta, that the pressure rise is increased up to some modest angle. But further increases in angle cause the pressure rise to decrease. At that time, we still did not have, however, any good picture of the overall flow patterns, nor did we have good methods for predicting optimum performance. We then began a series of systematic visual studies, and these quickly led to better understanding and to improved predictive methods. The bubble technique can show us what these patterns actually are. Let's start with the walls parallel. Notice how the velocity drops sharply near the wall, and in this region the particles slide evenly over each other. This low velocity region is called a laminar boundary layer. Now let's open up the diffuser to a total angle of about 7 degrees. The increasing area of the passage causes the velocity to decrease and the pressure to rise in the direction of flow. Watch a streak square in the middle of the passage. You can see the deceleration. Also notice the flow near the wall. You see a thicker boundary layer now, and it is no longer steady. Instead, you see irregular, time-dependent eddies. This kind of boundary layer is called turbulent. Even though some of the particles very near the wall do not have enough momentum to overcome the rising pressure, they mix with the particles farther from the wall, and are given sufficient momentum to keep moving in the downstream direction. If we increase the divergence angle of the diffuser further, something new occurs. Slow-moving particles begin to accumulate near one wall and then move upstream, forming what we call a stall. The mainstream is forced to separate from the wall and move around the stall. The pressure change caused by the movement of the mainstream is enough so that after a short time the stall washes out again. The whole cycle of stall buildup and washout then repeats in time. These unsteady motions we call large transitory stall. In this regime, the whole passage acts like an oscillator, even though the upstream flow is steady and symmetric. If we increase the divergence angle of the diffuser still further, the stall forms a relatively steady recirculating region on one wall. The mainstream separates very near the throat and hugs the other wall. If we move the mainstream to the opposite wall, it stays there. The pattern is what we call bistable. Usually we refer to this pattern as fully developed stall. If we increase the diffuser angle to high values, the flow separates from both walls. We observe a jet flow pattern. In studying fluid patterns, it's important to examine the whole flow field. Here's a diffuser with a lower divergence angle. A bubble wire near the surface of the flow shows an entirely unstalled flow pattern. But now we'll turn off this wire near the surface and turn on another one deep in the flow near the floor of the channel. This wire shows us that one corner of the flow contains a large stalled area. The wire near the surface still shows unstalled flow. If we'd used this wire alone, it would seriously have misled us about the nature of the flow pattern. Like any other experimental tool, flow visualization must be used with care to obtain reliable results. Knowledge about flow patterns is most useful when it's summarized in the form of a correlation. In the case of our diffuser problem, we can show the summary by this chart. It shows divergence angle 2 theta plotted versus length to width ratio, the length of the diffuser divided by the width, n over w. The chart shows us when we will find each of the 4 flow regimes you've seen in terms of the parameters. These lines indicate shifts from one flow regime to another. One point that needs emphasis about these shifts in flow regime is that it's very seldom that we can predict them on theoretical grounds alone. Even when we have a good flow model and a sound theory based on it, within a given regime we may not be able to predict where that regime ends. This is the case in the lowest region. In this region, if we stay well below the line of first stall, then we can use Prandtl's potential theory boundary layer model to make accurate predictions about the flow and about performance. But there is presently available no theory that will predict the transition, that is, this whole line. Higher up on the chart, in the other regions, the theories are not as complete, and there is no theory that will predict this line or the hysteresis region either. We might summarize all this as follows. When we first begin to study a problem in fluid mechanics, we may not even know the gross flow patterns to expect. After we've accumulated enough systematic information, in visual form or by other means, we can correlate the data, as for example on the chart. Finally, we can use the flow models so found as the basis for mathematical models, and if these are successful, we can then make paper and pencil predictions about a good many details. We can do that in this regime on the diffuser chart. The information inherent in the second or correlation stage is often useful for other purposes. Sometimes it tells us how to locate optimums, and sometimes it suggests improved designs. In the diffuser example, the lowest line in fact tells us the geometries that give maximum pressure rise for a fixed length of diffuser. The chart itself also suggests a way to improve short diffusers. Short diffusers usually mean wide angles, but wide angles mean separation, poor patterns, and poor performance. The chart suggests that perhaps what we ought to do is to divide up the passages into smaller passages, each one of which does not cross the first line of stall either this way or this way. Let's see if this idea works. Here you see a fully developed stall in a diffuser with a divergence angle of about 45 degrees. Let's insert an assembly of vanes designed so that each passage lies below the line of first appreciable separation on our flow regime chart. When the vanes are removed, the stall comes back. It's often useful to use more than one method of visualization. Let's use another technique to look at some of the things we've seen before, and also to study a new pattern of flow regimes, laminar-turbulent transition. For this purpose, a useful but very simple method is dye injection. All you need is a flask of adjustable height and a manifold with hypodermic injectors. Any dye can be used, provided its density is very close to that of the working fluid. Here you see the jet flow pattern made visible with streak lines of dye. Compare the pattern of the jet flow you see here with the bubble picture we saw earlier. The recirculating eddies, which you now see at the sides of the main flow, are made visible by seeping dye through holes in each wall. Dye must be injected with some care. If we apply the wrong pressure to the injectors, the dye will come out too fast or too slow. This causes jet instability, as you see here. Here's an apparatus to look at the flow very near the wall. The apparatus consists of a dye reservoir connected through a thin rectangular slit to the flow. The slit is only a few mils wide. The layers of flow extremely close to the wall are crucial in heat and mass transfer, in flow separation, and in the structure of the turbulent shear layer. The dye is turned on and seeps slowly through the slit. It moves upstream because the diffuser walls are at a very large angle and the flow is stalled. The walls are moved parallel. Now we are looking directly at the wall which contains the slit. The slit is near the left edge of the picture. Notice the smooth, almost glass-like appearance of the die. This is typical of a laminar boundary layer. Now we introduce effective trips. The flow over the irregular, streaky structure you see is typical of the wall layers of the turbulent boundary layer. The die streaks are actually zones of low-speed flow, and the clear areas in between are faster-moving fluid. If we remove one of the trips, we can observe the transition region between laminar and turbulent flow over the slit. In this region, you can see laminar flow side by side with turbulent flow. You can also see transient spots of turbulence moving down through the flow. If we move the remaining trip further upstream, the fraction of the flow which is turbulent at the slit decreases. Finally, the entire flow becomes laminar again. In the laminar turbulent transition problem, we again find several patterns of flow, and again the state of knowledge is different for each pattern. If we know the flow is laminar, we can calculate many fine details of performance from well-developed theory. If we know the flow is turbulent, we have workable approximate theories for a few simple cases. In a number of other cases, we also have good data correlations for such things as friction and heat transfer coefficients. If the flow is in the transition region, the theory is quite incomplete. As in our diffuser example, theoretical prediction of when a shift will occur from one regime to another is the most difficult thing of all. We have only part of the theory for a handful of cases and data correlations for a few more. We can predict results based on established flow models, but even in this very old and much studied problem, we still need correlations of data to predict the flow pattern that will actually occur. Let's consider one more example. Here's a flat plate parallel to the flow. A laminar boundary layer builds up on each side and forms a small symmetric dent in the velocity profile. But the dent is not evened out by viscosity. As the flow goes downstream, the two boundary layers interact to build a large oscillation. Here's the same flow shown by a single bubble wire downstream. Once again, a steady, symmetric upstream flow leads to an unsteady oscillation in the downstream motion. To predict the behavior of real fluid flows, we need to know the actual flow patterns. Flow visualization is one effective way to find them.